Hi viewers, welcome to LMS Solution. Today we are going to see about fuel cell battery supercapacitor powered EV vehicle. So this is a simulation model for a fuel cell battery supercapacitor powered EV vehicle system. So this system consists of fuel cell, battery and supercapacitor, and then here we have that control, right? So here you see that battery control, and this is known as supercapacitor control. Okay, so here we can go to fuel cell. So fuel cell rating is, you can see here, you can click that plot VA characteristics. So here you will see that rated nominal power is 10.2875 kilowatt, and then maximum power is 12.544 kilowatt, and nominal voltage is 41.15 volt, and current is 250 amps. At maximum power condition, the voltage will be 39.2 volt, and current is 320 amps for the fuel cell. Okay, and here the fuel cell is connected to the DC bus. Okay, so here you see that, right? So this is known as a DC bus or DC link. Okay, so that fuel cell is connected to the DC link via this boost converter. Okay, this boost converter going to be controlled by means of power balance. Okay, so according with the power requirement of EV system, the fuel cell will be supply the power. Okay, and next we have battery. So here you can see that battery is 48 volt and 40 Ah. Okay, here we are using lithium ion battery, and here we have two converter, boost and buck converter. So why it required boost and buck converter means, so it will be operating both direction. Okay, that mean when you have to supply the power, right, from battery to DC link, right? So that time it will be act as a boost converter, that means boosting mode, right? So when we need to have power from DC bus to battery, then this will be act as a buck mode. So that's why it need a both mode, both converter, boost converter as well as buck converter. Okay, that mean not to have the power flow in the both direction. Okay, so next, that supercapacitor. The supercapacitor is directly connected to the common DC link. Okay, so that means that capacitor will be connected across that directly connected to the that means DC link. Okay, so because the supercapacitor does not have any control in this, so according with power balance. Okay, that means, for example, we consider this is a DC link. So here we connect PV system, here we connect the battery, and in this point we are connecting supercapacitor, and this point we are connecting load. Okay, so here you will see that, right, the battery will be work in both direction, supercapacitor also work in both direction. So fuel cell will be supply the power according with the power requirement of this load. Okay, that means EV load. So here you can see that supercapacitor rating, the rated voltage is 291.6 volt, and initial voltage is 270 volt, and the rated capacitance is 15.6 farad, and then equivalent DC resistance is 150 milliohms, and series capacitor is around 108. Number of parallel capacitor is 1. Okay, so next you see here, this is the EV model of this EV system. Okay, so it going to be drive via driving cycle. So you have to provide driving cycle for that mean not to operate this EV model. Okay, that means this drive cycle will be provide the required power Okay, so according with this EV model will be work. Okay, so when we see the variation in the drive cycle, so the power of the EV model also going to be vary. So according with that fuel cell, battery and supercapacitor will be supply, or it will take the power from the fuel cell. Okay, so according with this EV power demand. Okay, so next we go with the control logic. So first we need to calculate load power. The load power in the sense the power of the EV model, and then here we have to compare with that. That will be converted into IF current value. That means we are taking the averaging of that power, and then we have that SOC of the battery. Okay, so here we have that filtered power or average power of the load, and here we have that SOC of the battery. That going to be processed via state machine control. Okay, so once you click inside, right, so have that state machine control. So this is state machine control program. Okay, so here you have that control logic here. So battery charging power here we have taken around 1500 watts. Okay, so SOC minimum will be, we are taking 60, maximum will be 90, nominal SOC will be 85, second nominal SOC will be 60. The power of fuel cell, minimum power of the fuel cell will be 850, maximum power will be 8800, and optimal power will be 1500. The maximum power of battery is 3400, and here you have to check the condition. Okay, that means SOC status. So if SOC is greater than SOC max, so that will be considered as state 1, and if SOC is greater than or equal to that means SOC nominal 2 and less than or equal to SOC nominal 1, then that will be considered as state 2. And then if SOC is greater than SOC nominal 1 and then less than SOC max, then it will be considered U of 3. That means this detailed status will be propagated from here. Okay, so just you have to take this one, U of 3. Okay, and then if SOC is less than SOC minimum, so that will be considered as state 3. And next you consider SOC is greater than SOC minimum and less than SOC nominal 2, then it will be take the output from the state machine control. Okay, if state equal to 1 and the load power, right, is less than fuel cell minimum, okay, power of fuel cell minimum level, then we are fixing the power of fuel cell which is equal to power of fuel cell minimum. Okay, in state 2, right, if state equal to 1 and U of 1 is greater than or equal to fuel cell per minimum and U of 1 is less than fuel cell per maximum, then you have to consider the P(f) of C equal to U of 1. That means we take that power requirement, that means load power, right, load power, that means load power which is equal, that means fuel cell power which is equal to load power. That means the fuel cell will fully supply that load power, that means EV load power. Okay, in state 3, state equal to 1 and U of 1 is greater than or equal to power factor, that means fuel cell power maximum, then we consider the fuel cell power which is equal to fuel cell power maximum. If state equal to 2 and U of 1 is less than fuel cell power minimum, then you consider this fuel cell power which is equal to fuel cell power minimum. And next you consider state equal to 2 and then U of 1 equal to greater than or equal to fuel cell power minimum, and that means U of 1 is less than fuel cell power optimum. Okay, U of nothing but the EV load power. Okay, then you have to take fuel cell power which is equal to fuel cell power optimum. So we have to check the state and then you have to check the EV load power with the fuel cell power So state will be determined according with the SOC level, and then the power reference for fuel cell determined according with the EV load power and state. Okay, so the state keep on changing according with the power will be taken from the state machine control. That means the state machine control in the sense here we are going to control the states of the system, okay, according with the EV load power associated with the battery. So now here we have that the fuel cell power reference, okay, otherwise called power for that to fuel cell files, power command for the fuel cell. So that going to be divided with the VFC, then we are getting current here, right? And then here we have VDC nothing but a DC link voltage, and then that going to be process, that means compare with the minimum voltage and compare with the maximum voltage, and going to be process via PA controller. So then it will be provide the reference current. So not reference current, that current requirement for a DC link voltage maintenance, okay. So that means it should be maintained around 260 to 285, okay. So for that it required some current, so that current will be comes from these two controller. So finally we have that required current value, that means reference current. So based upon this reference current, so you have to calculate IFC max and VDC, okay. So here we are calculating the IFC max and VDC, okay. So this is a control logic creating IFC max for that fuel cell and then VDC for that fuel cell, okay. So this IFC max VDC will be going to be connected here, okay, connected to this boost converter to control that fuel cell power and voltage and current, okay. So this is a fuel cell control. So next we comes with the battery control. So here we have that battery control. So just you have to measure the DC link voltage and compare with the reference voltage. So actually we need to maintain the reference that means voltage of the DC link is around 270 volt, okay. So that going to be compared with the DC link voltage, and it going to be processed with a PA controller. So this will be generate current. So this current known as discharge current. So and then the current will be multiplied with the -1 and processed via this filter, so then it will be known as a charging current, okay. So here we are creating the discharging behavior, and here we are fixing the charging behavior, okay. So this two will be that when so here you see that, right, two converters there, right. So VDC2 and I battery max, that mean discharging, right. So discharging will be linked with this boost converter, and the charging linked with this buck converter, okay. So the command, these two commands, right, I battery max discharge and VDC2, I battery max charge and V battery. So this detail will be sent to this boost converter and buck converter for a charging discharging operation, okay. So this is a control for a battery. So that means that boost converter and buck converter control battery for charging discharging, okay. So these are the control things, and also here you have the DC DAC converter. If the EV motor is considered as the drive with the PMS, permanent magnetic synchronous motor, okay, like that, right. So we need AC voltage, so for that only we are having DC DAC, okay. So now we are going to see the results. So here you will see here, right. So here you can see the power of fuel cell, battery, supercapacitor and load, okay. And then so here you will see that different color for the different power rate, okay, powers. So here you will see here, okay, once again. and then here you will see the result of fuel cell voltage, current and fuel cell power. And here you will see the detail of battery current, battery voltage, SOC of the battery power. And here you will see the supercapacitor current, voltage and supercapacitor power. Okay, and also you can see the fuel consumption of fuel cell and grams as well as LPM. And so this is a, that means line voltage and the phase current of the DC-DC converter. So now I am going to run this simulation. So you will see the results of the fuel cell, supercapacitor, battery and then EV load power. Simulation is started now. So now you see that, right? The fuel cell voltage comes around to 48 volt. The current is around 20 amps. Okay. Now you can see here, right? The power of fuel cell is around 1000 watts initially, and according with the variation of EV load power, right? So the red color, right? Red color is EV load power, right? So you will see that, right? According with the variation of EV load power, right? So the power from the fuel cell and battery and supercapacitor going to be changed. So initially we see that, right? The battery capacitor initially in charging mode, because initially there is no load. Okay, and supercapacitor have charging discharging during initial condition. So once the load is increased in the EV, right? So what happened, right? The fuel cell also going to be start generating, that means supplying the power. Okay, and during that sudden change, right, increase in EV load, right, what happened? The supercapacitor supplying the power. Okay, this point. And also battery also, this point battery will be start supplying the power. So because of that, what happened, right? The supercapacitor comes to charging mode. So it is in discharging for this period. Okay, after that it come for charging mode. So this supercapacitor will be going for charging, discharging according with that changes in the power balance. Okay, the supercapacitor here, the supercapacitor used to for supporting the sudden change in variation in the powers. Okay, if load power going to be changed, right? So when load power change, right, sometime it will be go above that power generation, right? So that time we need some power for supplying that load. Okay, EV load. So that time supercapacitor will be supply some power for short duration. Suppose EV load power is suddenly drop, right? So that mean what happened, right? System having some excess power. Okay, so that time the supercapacitor will go for a charging for short time. Okay, so that things you can notice here, right? So it go for charging, it go for discharging, and then after that it will be comes to 0. So again it will be going for charging and then discharging and then comes to 0. And battery also, right? Battery will be charge and discharge according with the EV power demand. Okay, and also fuel cell demand and also that state machine control. Okay, so here you will see that variation of fuel cell voltage, fuel cell current and fuel cell power. So here you will see that variation of current of supercapacitor, voltage of supercapacitor, power of supercapacitor. So this is a variation of battery, current, voltage, and this is power. And see that SOC, right? So SOC is maintained in between around 65% to around 60%, okay, for the particular drive cycle. Okay, so this is a result how that energy management happened between fuel cell, battery, supercapacitor and the EV load, right? So you can see here, right? So the power balance will be maintained always in the system. Okay, and also here you will see that this, so this is a consumption of fuel. Okay, so you will see that here, right? And then this is a fuel consumption in terms of LPM. Okay, so this is a result of fuel cell, battery, supercapacitor driven EV system. Thanks for watching our videos. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you so much. Bye bye.